Wait, joining in a second.
Oh, yeah.
Oh, okay. Well, I just started recording.
Yeah, here's Andre right on cue. So
Perfect. All right. Do you want to get started?
Yeah, I can do that. Let's see if I can share my screen. I'll just share my whole desktop. Does this work? Do you see things?
Yes, looks great.
All right, great. What's that?
That's exciting.
Yeah, lots of stuff.
Yeah.
So I've been sort of busy over the last like 3 or 4 weeks building this end-to-end test framework for Tendermint, and I thought I'd just give everyone sort of like a walkthrough of like how this works and what problems we're trying to solve and these sorts of things. So feel free to like ask questions as we go along and so on. I guess I'll sort of start off by saying like what end-to-end tests actually are and like what problem we're trying to solve with them, right? So there's this like traditional concept in like software testing called like testing pyramids, I guess, which is basically like made up of like 3 kinds of tests, right? You have unit tests, you have integration tests, and you have end-to-end tests. And these are sort of like at different layers of the stack in a way, and the unit tests are like the ones you're gonna have the most of, right? These are the ones that test like one component in isolation. And these do like very, very sort of comprehensive testing like all possible inputs against all possible outputs, like making sure the thing does what it's supposed to be doing. And these are usually sort of fairly cheap. You can run a few thousand of them without it being too expensive. That layer above that, you have integration tests, which are when you sort of combine a few components together and make sure they work well in tandem. So in Tendermint terms, this will be maybe like spinning up a reactor along with like a block store and an evidence store, and like making sure like given certain network inputs, it actually puts things in the block store, puts things in the evidence store, and like it behaves the way it's supposed to. At this level, like you wouldn't do that comprehensive testing. There are certain things you can't do. Like for example, if you're building something that depends on like storage, you may not be able to provoke a hard drive failure with like an actual integration test, because like provoking a hard drive failure is really difficult. So like at the unit test level, you'll be able to sort of provoke a hard drive failure by mocking the storage layer and returning a hard drive error. At the integration test level, you wouldn't be able to do that, right? So the number of things you can test at each level gets reduced. And so at the highest level, the end-to-end test level is where we're going to have like the least amount of coverage. And these are also going to be really expensive to run, but they're still very useful in the sense that at this level, we're really sort of spinning up the whole system. Like we're taking the Tendermint binary that we're shipping to our users and we're starting them up. We're starting a whole network, and we sort of make sure the network operates the way it's supposed to. And this is primarily in order to like make sure all of these different components actually work together in a reasonable way. We've had quite a few bugs lately where certain functionality was just completely broken. So for example, state sync was completely broken because we didn't propagate Genesis state completely. And even though we had integration tests and unit tests, they were like all passing because we weren't sort of looking at how state was being propagated through the entire node. We didn't catch this bug. And so end-to-end tests are really a way to try to discover these sort of like systematic bugs, right? And make sure that the whole system as a whole works. And this also means that end-to-end tests will typically be black box tests. We're not going to be looking inside the Tendermint node and like see what the node does on the inside. We're not even going to look at what the network does internally. We're not going to look at the peer-to-peer traffic or anything. We're just going to spin up a network and we're going to see if the network exhibits the behaviors we expect the network to exhibit. So one example would be sort of like if you spin up 4 validators, are they able to reach consensus? Are they able to produce blocks? And do the blocks contain what they're supposed to contain? And the way we would typically inspect this is just by call RPC on all nodes and see like, okay, does the RPC results match my expectations, right? So does that sort of make sense to everyone? All right, cool. So then the purpose of this testing is to be able to actually construct these networks and sort of like make sure these networks function the way they're supposed to, and to verify that a bunch of like invariants hold. And so some of the complexity in Tendermint really comes from the combinations of configuration options, right? So take, for example, fast sync and state sync and the consensus reactor. When a new state sync node comes online, it's first going to state sync, then switch over to fast sync, and then switch over to consensus mode. But we have 3 different versions of the fast sync reactor. So like we need to make sure this works when we're using the V0 fast-sync reactor, the V1 reactor, and the V2 reactor. And we want to make sure these work both when we're state syncing and when we're not state syncing, and also when we're not using fast sync at all. In all of these sort of situations, the network should still be able to sort of reach consensus and start producing blocks, right? So we need a way to be able to produce networks with all these combinations of configuration options. And this blows up pretty quickly because like I even with like the sort of few configurations options we're currently supporting, there's like, I think 3 million different combinations of how to set up a node, right? And we want to sort of get as good coverage as possible so we're able to actually test most of these combinations in some way. So we built this like end-to-end testing framework, which allows us to sort of specify what a network should look like, and then sort of spin up one of these networks and sort of put it through its paces and then run a test suite against the network after it sort of reaches equilibrium and stabilizes. And this manifest looks like what you can see on the left-hand side here. This is like a fairly simple example of one of these manifests. So what we're doing here is that we're specifying one seed node, and we're specifying 4 validator nodes, and we're specifying 1 full node, right? And so we're saying that this network should start with an initial height of 1000, which will be specified in the Genesis file. It gets the application, which is a simple key value store application, gets some initial state in the Genesis file, foo equals bar. We're setting up one node running it in seed mode. And then the first validator, we set that to use the seed node as a seed. And we set this node to run, to take state sync snapshots every 5 blocks. For validator 2, we're configuring this to use Badger DB instead of using like a default level DB. And we're also setting it to not to instruct the application to not persist data. So this will allow us to sort of test things like, if this node is restarted, will this node actually come online again, like replay all these blocks and be able to catch up even if the application isn't persisting state. Validator 3 runs using Unix sockets for the ABCI communication. And it also uses a remote KMS instead of using sort of like a local key that's configured for the node. And for the 4th node here, we're asking it to only retain blocks, only retain the last 3 blocks. And we're also setting up what we call a perturbation, which means that we're going to try to actually disconnect this node and see that it's able to actually reconnect to the network after being disconnected. And then finally, for the full node, we're going to start at height 1010. It's going to connect using persistent pairs instead of using the seed node. It's going to enable fast sync version 2, and it's going to enable state sync. And so what we're really testing here is that we're setting up a set of 4 validators, allowing them to sort of like reach consensus. And then after they produce 10 blocks, then we start up a full node, which will state sync and then fast sync and then join consensus and sort of like keep catching up with the blocks. Does that make sense to everyone? Any questions?
I have some questions about the KMS.
Sure.
So are you running the Rust, like the occlusion KMS?
No, in this case, like both the application and the KMS are just custom built for this test framework.
Got it.
Because we need to be able to control it in certain ways. Like we may want to simulate, for example, what happens if the KMS falls offline and comes back online, things like that. Yeah,
I have a question.
That makes sense.
Sure, go ahead, Bess.
Can you add, is it possible to say add, you have 4 validators in this case, a 5th validator, let's say like 500 blocks later?
Yeah, that's absolutely possible.
Okay.
So I can show you like a little more complex network later, but I figured we'll just start with like a fairly simple and like understandable one to begin with. But it's absolutely possible to like change the validator sets, change their priorities, and like have them join or leave the validator set and so on. We can absolutely do that.
Cool.
So now that I have this manifest, if I want to like run a test with this one specific network, we have this test runner that will go through a few stages. So the first thing this tester is going to do is it's going to run a setup phase, which is where it generates configuration for the network. It's going to set up Docker Compose, which is what we use to run the network. So it's going to set up a Docker Compose file. It's going to generate like keys for all the validators. It's going to generate like Tendermint configurations, ABC application configurations, and so on, and set everything up. Then this start phase will just start all Docker containers in the sequence they're meant to be started in, and sort of like start some of them delayed if they're instructed to be delayed, and so on. Then we start generating a transaction load where we just generate random transactions and submit them to the network and make sure the network's actually able to process transactions. And this sort of happens in parallel with the rest of the stages. Then we run any perturbations, which would be maybe restarting a node, killing a node, disconnecting it and reconnecting it, and so on, and making sure it's actually able to sort of rejoin the network and go back to a stable equilibrium. Then we wait for a few blocks to be produced and wait for like all nodes to catch up to like a common height. And after we do that, then we have a set of test cases that we run against the network. And these test cases will like test certain invariants. So one example would be it'll test that all nodes contain the same blocks, right? The block headers are the same across all nodes. Or it will test that validators have actually proposed for the heights that they're supposed to be proposing for, right? So we're testing all these like broad network invariants. And then finally we stop it and we just clean it up and like shut down the containers and like remove the files and everything. And the runner also supports running these like individually. Like you can specify in the command, I just want to set up a network. I don't want to start it or anything, just generate a configuration. And I can start it up and I can sort of inspect it myself and everything. You don't have to run the whole sequence. This is really useful for like debugging if you're trying to fix a bug and you want to see like how the network behaves in certain situations. But in the default case, it will just run through all the stages automatically. So if we now take this network and we run it, I basically just have this runner command and I specify the path to this network manifest. That's all I do. And you can see the first thing it's going to do is to generate these files. And it's going to start the initial network nodes, which are like the ones that are scheduled to start at the network initial network height. It also starts like producing this transaction load. You can see that node CD101 came up and the 4 validators also came up, and then we wait for the validators to reach the initial height to like produce the first block. Once that's done, it's going to wait until height 1010, which is when we're scheduled the full node to start. And once that starts, that full node is going to first state sync and then fast sync and then reach consensus. And so we can see here, like after 20 seconds later, that node was able to actually fully state sync, fully fast sync, and join network, and it's now at height 1014. Then we try to disconnect this node validator 04 because we specified we wanted to try to disconnect that node and see if we can reconnect. The node was able to recover. After that, we sort of like done everything we need to do with network. So at this point, we're waiting for all nodes to reach a common height. And then we're ending the transaction load. And once that's done, we run the test suite. And so the test suite, we run like a whole bunch of tests, and these tests are run against each individual node in the network, making sure that node satisfies its invariants. And this will be done with like all nodes. And once that's done, we just clean up, remove the container, shut everything down. And that's pretty much it for like a simple run. Any questions on that?
This is so cool.
Yeah, thanks. It's pretty neat.
What kind of invariants do you test?
Good question. We can have a look at like the actual tests we're running. So right now we're not running like a ton of tests because we just want to like get some basic up and running, and then we'll sort of add stuff as we go along. But like one example here is this test that makes sure that like validators are actually proposing blocks when they're supposed to be proposing blocks, like on the validator schedule, right? So this is just a normal like Go test case. There's nothing like not like fancy about this. We use this normal Go testing framework. What you first do is you have this like utility function that fetches the entire blockchain. It's nice to have a utility function for this because some of the blocks may be pruning blocks, some of the nodes they may have run state sync, so not all nodes will have the full history. So we have this utility function that just finds an archive node in network and downloads the entire block history from that node. And then we have this utility function here, test node, which will be run in parallel for each node in the network. And it takes in sort of the node manifest. So this test will know which node it's looking at and what the configuration of that node is. And it can change its behavior based on that configuration. And in this case, if a node is not a validator, then we just exit, because we only care about validators, because only validators propose things. Like full nodes never propose, right? And then we set up this validator schedule, which is just a utility function to simulate the validator schedule, to like look which validators are scheduled to be proposing blocks at which heights, right? So this also to see like which validators should be proposing blocks for like height 1005 and 1006 and so on. And so once we have this schedule, we just iterate over like all the blocks in the blockchain, and we check like if the node we're currently looking at was scheduled to propose a height 1005, for example, we'll look at the block 1005 and say, okay, did this node actually propose this block? And then we can see, we can keep track of both if they actually missed proposing when they were supposed to propose. And we can also like look at like if they proposed when they shouldn't have proposed, right? And then we just have this like normal assertions here. So in this case, we have some tolerances to like allow them to like misproposing a few blocks, because if you're sort of disconnecting a node from network and it's reconnecting 10 seconds later, it's going to misproposing if it was scheduled to propose. So we allow like some proposals to be missed. But we obviously want to like propose maybe 80 or 90% or something of what is scheduled to propose. Does that make sense?
So it's like kind of a goal-based API for testing node level properties.
Yeah, more or less. And these tests are actually pretty simple. Let me find a different test that's a lot easier, right? So this test right here tests that the initial state that we specify in Genesis has actually made it into the application. So if you look at the demo manifest that's specified here, initial state foo equals bar. And this will be sort of set in Genesis, and the application should be given this during init chain and should import this like when it's initially set up. And so this test here will just make sure that actually happened, right? And the way to make sure that actually happened is to query the application. Do you have this data that was set during init chain? And so what we're doing here is that we call this test node function that runs for like each node in the network. And then we say if there's no initial state, just a route. And then we have this convenience function that gives us an RPC client for the node. And then we just go over the expected initial state, and we run an ABCI query against that client using the RPC client for like each of these initial key value pairs, and just make sure they're present, right?
And how many of these tests can you run in like a minute?
Yeah, so now I think we have about maybe 10 or about 10 tests now, and are running this in this test net here, which has 6 nodes, took 2 seconds.
Okay, but the tests are not independent. It's like it's not a new network per test.
No, these all run once network is stabilized. Because these invariants should hold in any network. The only thing you have to be careful with here is that the test shouldn't write anything. As long as the tests don't write anything, then like they should all be independent, more or less.
So they could only be dependent on the stabilized state.
Yeah. Now note that this network is still going to be running, it's still going to be producing blocks, but those blocks will be empty. So we have one test, for example, which checks that the node contains the blocks it's supposed to contain. But this is obviously going to have to read the node status to see like how far along are you, and then like run the tests on that, right? Rather than sort of like having some predefined constant is checking.
What was the hardest test to write?
Well, for the actual tests, we don't really have that many tests yet. I guess the hardest one are these validator tests, because I had to just simulate the validator schedule, like being able to, like given a set of like initial validators and given a set of validator updates returned by the application, calculate what the validator set will be at like each height. So it was sort of tricky to just write a simulator, but it turned out to be kind of simple once I familiarized myself with the validator set functionality we already have, because like the Tendermint node already does this. This is how Tendermint node figures out who should be proposing, right? So the logic was there. I just had to like wrap my head around it.
A quick question, Erik. So one thing that we do in the, I wonder if it's applicable in this kind of test suite is in the SDK, we have we introduce like randomization based off a seed value.
Yeah.
Do you think it would be beneficial to maybe either simulate some sort of state or simulate some sort of action that a validator or full node can do randomly based on some seed value to kind of like really broaden the test coverage of this?
I'm glad you asked. That's the next level we have.
Cool.
So what we're looking at now is just the test runner, but on top of this, we have a generator which generates random testnets, which can generate like 100 different testnets in different configurations, or 1,000 different testnets in different configurations, and we can run all of those, right? I'll get back to that.
Okay.
But at this point, I just want to like start with like just a static manifest and just like get sort of the flow of the framework, right? And I will also say like I want this to be really like friendly to developers. So like if you're debugging a bug, you found a bug in one of these networks, right? What this will allow you to do is, let's say I just want to start this network, but I don't actually like, but I want to keep it running so I can look at it and I can interact with it, right? So I can just run the runner again with the start command, which is now going to go through all this like sequence again by starting up nodes and everything. But after everything is started in Docker, it's just going to exit. It's not going to clean up everything. It's not going to run any perturbations or anything. It's just going to like let it sit there running, right? And once it does that, I can just set this environment variable in the tests, in these like unit test files, which just gives the path to the manifest that's currently running. And once I save that, I'm actually able to run these unit tests interactively from my editor. Right, so now we have this network running. If I do Docker PS, we can see all the nodes are up and everything. I can curl them if I want to. So I can like curl a node, I can look at it, like everything's just up and running. And if I want to run a test now, I just run test. That actually executes against the running network. And so if there was a bug here, like if this failed, I would get test failures, right? So this sort of allows me to pretty easily sort of write tests while the network is running and like make sure they're right and so on, without sort of having to like run this like heavy test runner for like every single iteration. Okay, good. Let's see. Yeah, so there's I don't know how much I want to go into depth on like the ABCI application we're running on KMS and stuff, but the ABCI application is basically just a simple key value store that like saves its data to JSON files and takes static snapshots and like implements sort of very basic functionality, nothing too fancy. And the KMS is also just something that uses like the file PV in Tendermint and just uses that to like sign blocks remotely. So nothing very fancy. We can take a quick look at like sort of the different options that we have for these manifests to see like what functionality we can actually do with these manifests. So we have this CI network, which is what we run on like every single pull request in GitHub. So on every pull request, we don't want to run like 100 testnets because that's going to be too slow. So we sort of pick like one testnet that's sort of representative of like a broad range of functionality, and we just run that one testnet. So this is a little bit more involved. You can see here that we're sort of starting in Genesis with like a single validator, and then we're doing like an init chain update to like add some more validators to the set, and we have like validators joining at like height 1010 and 1020 and so on, with like different priorities and stuff. We have two seed nodes that sort of set up a mesh with each other to make sure like the seeds are able to actually exchange peers. We set up a bunch of validators with like a bunch of different options. We have like different perturbations, EBCI protocols, KMSs. We try all the different databases that we support in Tendermint. We have some blocks that are running with like a truncated block history. We have some nodes that are running with no persistence. We have some blocks that are just only keeping the last block and like discarding everything else. Just running like validators like a bunch of different manifests. We had a bunch of different combinations. We also tried like fastsync v2, we tried fastsync v0, we tried statesync on, statesync off, and so on, and see that like all of these different nodes are able to actually catch up to the network. And so if we want to look at all of the different options that we can use in the manifest, specified here, I think we covered like most of the global ones. We can run them with IPv6 or IPv4. We can set the initial state for the application. We can set initial Genesis validator set. We can set validator updates, either for the init chain update or for like specific heights. And on a node level, we can start them in different modes, like we have validators, full nodes, and seed nodes. We can set them to use persistent pairs. This allows us to set up different network topologies. So down the road, we want to be able to set up, for example, sentry nodes and sentry node architectures. We want to set up nodes that are behind NAT gateways. We want to set up nodes that use UPnP for discovery and so on. Like we didn't build this in the first iteration, but we want to be able to set up like arbitrarily complicated network topologies and test those. But right now we only set up a flat network, and you can use persistent pairs or seeds to like discover nodes. We can vary the database used to persist Tendermint data. We can vary the ABCR protocol and the KMS protocol. We can start nodes at specific heights. We can vary the fastsync reactor, either disabling it or using either one of the three ones we have. Enabling or disabling statesync, enabling or disabling persistence on a certain interval, statesync snapshotting, block retention, and these sort of like perturbations or disturbances. So those are sort of the functionality that we currently support. But there's a bunch of other stuff we want to add on here. For example, I think Marco just put in like these SECP keys, or however you pronounce them. So like once he does that, we probably want to add an option here for like using different key algorithms on these nodes. So we're able to like exercise those. And we're going to sort of add on more options here as we go along to like test more functionality, right?
SecP, by the way.
Oh, SecP, yeah, thanks. But yeah, any questions on that? Great.
Actually, I have kind of a funny question, but is perturb a standard term in this kind of testing, or is that an Erik special?
I guess it's the physicist in me speaking. Like in physics, like a perturbation is when you sort of take something away from a stable equilibrium. And that's kind of what you're doing here. You allow the network to reach an equilibrium, and then you sort of like bump one of the nodes, and you wait for it to sort of come back to equilibrium. And that's kind of called a perturbation in physics. So
I like it a lot. I was just wondering.
All right. Yeah, I'm not really sure, like you could call it like a disturbance or something, I suppose, but I thought it was like appropriate given the context. Okay, so what I will say, like one thing you'll notice here is that this is very much happy path testing, right? We are not really looking at how the network will fail in certain failure scenarios, right? We have some very basic things, we like restart nodes, we'll kill nodes and so on. But apart from that, we're not like doing very sort of comprehensive testing of like how the network acts to like malformed inputs and things like that, because that's not the job of end-to-end tests. The job of end-to-end tests is to make sure that the system as a whole sort of exhibits the overall behavior we would expect under like most normal circumstances. For like comprehensive chaos testing and stuff like that, that will be either integration tests or unit tests. Those are not really appropriate at this level, right? And they're also very difficult to provoke. Like it can be hard to sort of like introduce malformed peer-to-peer messages when we're running nodes that are actually correct, right? How would you do that? You would have to like inject network traffic or something, which is not trivial to do. So this is mostly just like to make sure we didn't completely break something, right? And so now that we have these like manifests, this goes back to what Bess was saying earlier. Like now we want to like generate these manifests in like a bunch of different random permutations, right? And so we have this network generator for this. I can bring it up quickly. So when we're sort of generating these networks, there's a few different things to take into account here, because like the number of combinations just really explodes pretty quickly. We have like over 3 million combinations of settings, right? So we really need to like start constraining this a little bit. And one way to do that is to like look at network level settings versus node level settings, right? because things like the database can be varied on a node level, but things like the initial height, for example, is global for the entire network. Like you can't have some nodes starting at a different height than other nodes, like the whole network starts at one fixed height. So for all the settings that are network-wide, we try all combinations of settings, right? We do an exhaustive search of all combinations, but that's currently not that many. Like we're trying 3 different topologies, either a single validator, 4 validators, or a larger network with about 15 nodes. And we try with IPv6 and IPv4, and we try with initial height 0 or initial height 1000. We try with and without initial state, and we try with validator specified in the Genesis file or specified in the init chain call. These are like the only like network level settings that really vary. So this turns out to be like 48 combinations. So we're actually generating 48 testnets there, which isn't like that many. But like once we add like a single option more, we're doubling the number of testnets. So if we add like one more option here, that's going to be like 100 testnets. If we add one more, we're getting like 200 and so on. So this blows up quite rapidly. And then for the node level settings, we just generate them randomly. We just pick a random option and make sure that the settings are sort of coherent, which means that like if we randomly choose to prune blocks, we also need to make sure that the application actually saves its state. Otherwise, it won't be able to come back up and restart it, right? But apart from making sure a few of these constraints are satisfied, we just pick random options and just generate them completely randomly. So I can show you an example of this. I just basically run build generator, and I'll give it an output directory. And now I can go into this directory here, and we can see that I generated 48 networks. So it's going to generate these 48 networks. That's going to be like, for each combination of options here, we're going to have a different network. So we're always going to have a single node network with IPv6, and we're always going to have a single node network without IPv6. We're always going to have a quad or like a 4 validator network running with IPv6 and one running without, and so on, right? And this gives us like a fairly sort of comprehensive view of, or like fairly comprehensive testing of like all the interactions. It's not like an exhaustive search, but it's a good enough search, I would say, of the parameter space. And in addition to that, we also have like a small script that just allows us to run like all of these test nets without sort of having to run them manually. The generator can also split this up into groups. This generator is used for a nightly CI job. So like every night we'll run like all of these test nets and just make sure like they work on master. But when we do that, we split this up into like 4 groups, and we run these 4 groups in parallel, right? So yeah, I think that's pretty much it. Like that's a really sort of quick walkthrough of like our end-to-end testing system, at least on early iteration of it. So what do people think?
Really awesome. Really cool.
Thanks. I think this is really useful. Like I've already uncovered, I think like 5 or 6 issues and like actual like node panics or like concurrency bugs in reactors and stuff.
Awesome.
So I think these things will turn out to be really valuable for sure.
Erik made
Very
an
cool.
interesting observation earlier that this testing system has had fewer, I guess, like false negatives than a lot of the integration testing stuff also.
That's
which,
true.
Erik, do you want to just say a sentence more about that? I thought this was very interesting.
Yeah, so a lot of our integration tests, right, where we just spin up 2 reactors and just make sure they can communicate with each other and just pass them like inputs and outputs, those tend to be pretty flaky. Like we'll pretty often have like non-deterministic failures where things just like because of timing or because of like random fluctuations, they just fail, right, which is super annoying. These end-to-end tests haven't really had that behavior. And I think the reason for that is actually just the Tendermint is kind of robust, right? It'll sort of tend to like recover from like failures and like converge on like a stable network. And I also think it's because like the time scales for these networks are much larger than in integration tests. So when we start up a new node, we like give it a whole minute to be able to actually come online and catch up to the network. While in integration tests, you may just give it like 500 milliseconds. And if it hasn't happened yet, then we just give up, right? So I think it's a combination of those two. I think it's because the whole node will tend to be more robust and do more sort of retrying and stuff, and also because the time scale is just much larger.
Can I ask a question?
Go ahead.
Can we go back to the tests?
Yeah, absolutely.
Maybe app test was pretty cool.
Yeah, let's see. There we go.
Okay, so the description of these invariants, how would you, what's a one-line description of these invariants? I guess that's the comment. Test at any state given a genesis has been made into the app. But what is the invariant?
The invariant for this one specific test is that if the testnet, or if we specify initial state in Genesis, every node should have that state.
Mm-hmm. Is this safety? This is agreement property.
Yeah, that's sort of, it depends on like
Well, that's what
how you define
Zarko would
that.
say, but Zarko's not here, so you can call it whatever you want. But
Yeah.
if he were here,
But it's
this
like
is I'm not going to do a Zarko impression, but he would surely do his own Zarko impression and tell you that this is agreement.
Yeah, that may well be, sure.
So, but it seems it's pretty serious, right? We kind of needed to do this. This is an important invariant, right?
I would say it's important because like if you're doing upgrades, during the upgrade, you're going to export all of the old state and import that into the new chain. If this doesn't work, your upgrade is going to be worked.
But actually, would you ever ship any, well, yes, because the production network is kind of past that now, right? Is that what you're saying? So
this will only happen when you're starting up a new empty node, which needs to like bootstrap from Genesis.
Well, one question I would have is, would you ever ship software in which this test failed?
No.
Right? So it's pretty important.
Yeah, I would say so.
And it's important for pretty much like every Tendermint implementation, probably Tendermint and Rust as well.
Yeah.
Interesting.
And I will also say that like these tests, because they only speak RPC, if this network was running Rust, the same tests would still apply because it's just speaking over RPC.
Right? Interesting. Okay, so the reason I sorry for the unstructured dialogue here. So we have certain tests that we didn't used to have this, but increasingly we are having this, sets of tests that apply to both Tendermint and Go and Tendermint and Rust. So one example is the like client, right? And that's like super specific, right? It's very, very refined. I guess it's at the lower in your pyramid.
Yeah.
Okay. And those are, we're trying to figure out where to move them. It's kind of a pain. We've been moving into spec repo because this is like the idea that this is important for everyone. Do you think eventually we'll have like tests reflecting the invariants that you're enumerating in your end-to-end test in the spec repo? Or is it more of a Tendermint and Go specific thing, or does it depend?
I think sort of the tests themselves, we could probably extract out into some like implementation agnostic thing, because
like TLA?
I don't know if like TLA would necessarily be the thing, because this we're not running this against simulated inputs. We're running this against actual live inputs. That's the whole point.
But wait a second, TLA with MBT takes simulated inputs and runs it on code.
So Sean, we're exploring that area too, but we're kind of want to come at it from both directions, right? Like we want to ensure that kind of like, you know, our implementation conforms to the specification and to the specification modeled in TLA plus, right? And so Anton is like, you know, taking that approach to model, or he's not doing the modeling, but he's taking the models for the light client and building model-based tests for them, right? And that's kind of coming at it from one side. I feel like this end-to-end testing piece is almost like coming at it from the other direction, right? Which is like you know, just making sure that like invariants hold at like a network level rather than like sort of making sure that anything conforms to a specific model.
Right,
so I agree with that.
So we specify the light client, and it's like super specific. And we do like one light client or like a couple of providers. So it is kind of like it has a network, right? Because it is like a network invariant. And again,
Yeah.
I'm going to apologize profusely for my unstructured dialogue here. I might be jumping around between topics. Okay.
No, but I feel like these sorts like model-based tests would be at sort of integration test level, because that gives you more ability to inspect what you're testing. You can look inside it.
It depends what the
do that with
invariants are, it seems, is what I'm seeing.
Yeah, but with like model-based testing, you would do sort of comprehensive tests, right? You would test like a whole bunch of different inputs, and that's usually better suited for unit test to integration test level, because they're cheaper to run and they're much faster. And
but you ran these in 2 seconds. How many seconds did you need?
but these are 10 tests. Like if you generate like a TLA plus thing, you're gonna generate like 1,000 inputs or like 10,000 inputs. And like some of those inputs may be network levels. Now we have to like actually run 10,000 networks, and we don't want to do that. So
no, that's too many.
So I feel like those are better suited for like integration test level, where you can inspect the thing more closely and you can spin them up much faster and sort of set up more controlled environment.
Mm-hmm.
But I will say, like, these sorts of tests, you can really think of this as more of like RPC tests, really, right? And so if we're saying that the RPC interface is really sort of part of the Tendermint specification,
maybe
then maybe it makes sense to have these like in a common place, just to make sure that RPC behaves correctly for and network behaves correctly, right?
But I mean, maybe it is about RPC, but again, when I was like being Zarko a while ago, I felt like the invariant that was being asserted there is agreement, which we do have tests for, right?
Yeah, but again, like the thing is, so if we did this sort of at the integration test level, right, then again, to take the state sync example, we have fairly comprehensive tests of state sync at the integration test level, but it still broke, right? And it didn't break because we didn't have tests for state sync. It broke because the way state sync interfaced with the rest of the system didn't work. And that's what these end-to-end tests try to solve, right? There was nothing wrong at all with the state sync system, but there was a bug in the flow of data from one component to the other.
I see. Okay. Thank you.
Yeah, totally. Any other questions or anything? Or well, cool. I guess we can about wrap this up then. Thanks everyone.